Hello, everyone. I'm Xinyi, and I've come from to Eindhoven. I'm so sorry for my voice because I'm not feeling very well recently, especially in the throat. So, yeah. And let's begin. So, there's a urgent global need to reduce carbon emissions, and this has intensified the focus on transition to sustainable energy solutions. And residential heating accounts for approximately 10% of national emissions in the Netherlands, where the predominant use of natural gas for home heating is a key factor. So we need a more detailed model to simulate a group of homeowners' decision-making process of heating. And let me introduce agent-based models. An agent is an autonomous individual element with properties and actions in a computer simulation. An agent-based model is the idea that the world itself can best be modeled by using agents and environments and descriptions of agent and agent-environment interactions. The concept of agent-based modeling is one of the best ways to describe the complex system that we see around us. So why we choose agent-based model? Agent-based models are now often used in energy-related investments or adoptions modeling to examine producer and consumer behavior. Compared to previous modeling techniques like equation-based models, agent-based models make access to fine-grained data easier while also enabling a thorough and accurate description of a complex system, encompassing agent behavior, social interactions, and their physical, technological, and economic context. So the agent-based model comes from a bottom-up initiative. By applying agent-based models in collectives, it is possible to develop more accurate models of the social, economic, technical system, and to explore the potential impacts of different interventions on the community and the energy system as a whole. Next, let me introduce my model structure. This model is to simulate the residents' decision-making of heating system. And the goal is to examine the adoption dynamics of sustainable residential heating system, focusing on the transition to gas-free communities. We can first see in the circle, each agent is characterized based on statistical distributions that reflect social demographic profiles and social clustering data, consistent with real-world demographics. And the internal state of an agent encompasses a range of parameters, which is marked as orange, such as income, savings, environmental concern, energy efficiency concern, and more. Also, each agent would have its own thermal needs and energy usage pattern. We assume that there's a social network here, which means agents would be affected by their neighbors. They will communicate with each other, so the decisions will also be affected by their neighbors. And then the agents are programmed to evaluate and possibly adopt energy technologies at each simulation step based on their decision-making rules. The state evolves as the agent interacts within the social network and make decisions based on the decision-making rules. So here we include the opinion dynamics. The agents are faced with three primary decisions: to invest in a gas-free heat pump, or to district heating with gas, or to keep current heating system, which means no invest. And these decisions are shaped by the agent's different concerns and the financial assessment. And we have a feedback mechanisms, and which are used for reflecting the evolving preference and social norms. as agents interact and make investment decisions. The next step is the parameter setting. This table compares 3 heating system investment options. The first one is heat pump. The heat pump has the highest initial cost but offers near zero carbon emissions, making it highly energy efficient here. And then there's a district heating, which has a moderate initial cost and medium running cost, with emissions varying based on the energy source. And we assume that the source area is not gas-free. The no investment option means residents make no change to their heating system, so it has no initial cost, but it's the least efficient and most environmentally damaging due to high emissions and energy consumption. And Table 2 details the parameters and agent profiles used in the model. Household characteristics like income and environmental concern play crucial roles in the determining investment capabilities and also preference for sustainable choices. Thermal net is calculated based on the number of occupants and their vulnerability, while insulation quality affects the preserved efficiency of heating systems. And energy usage patterns and investment cost for different heating options significantly impact the net present value and the long-term benefits perceived by households, which is in the economic aspect. And by simulating these parameters, the model captures the diverse decision-making processes and preference of households. The decision-making step is quite important for getting ideal results. And here's some general steps for the basic decision-making process in the agent-based models. And in the model, residents need to choose the most suitable one among multiple investment options. So it often involves 4 steps. The first one is observation. Agents observe the environment state and other agents' actions through sensory inputs or data inputs, such as direct observation or information exchange. And then is the evaluation. Agents evaluate their current state and available options by assessing potential consequences and rewards associated with different actions or strategies. The third step is the decision rules. Agents select their actions using decision rules or algorithms you choose. And the last step is the action execution. Agents choose an action to execute. The decision rules, we said, is using the theory of planned behavior. So in the model, agents make decisions based on this theory. The theory of planned behavior explains human behavior through 3 attributes: attitude toward the behavior, which is the first column, and subjective norm, and perceived behavioral control. The intensity of the behavior and the individual's commitment to action are influenced by the weighted contributions of these attributes. The process begins with a range of input factors that influence an agent's beliefs, attitudes, and perceptions. Also, we add the social pressure here, which means the agent in the social network will be affected by their neighbors. These 3 attributes combine to form the agent's behavioral intention, which is the precursor to actual behavior. The stronger the intention, the more likely the agent will invest in a heating system. If the intention is over the threshold, then the agent will choose this decision. Here's our simulation process. The simulation begins with 1,000 households, and each household is uniquely defined by a set of attributes, as we have already introduced in the agent profile in the table 2. And the core of the simulation runs through 15 steps, representing a span of 15 years. Each cycle or each step is a crucial period where households make decisions, and agents will update their decisions based on various factors, including the recent choice made by their neighbors. Besides, households annually reassess and update their intentions and financial estimations, leading to potential changes in decision-making. Now here's the result. The result shows an increasing preference for gas-free heat pumps, indicating a collective inclination towards sustainable options. And heat pumps show higher adoption rates compared to gas heating, district heating. But the simulation may have an inherent bias to environmental action, influenced by the weighting step. We're weighting environmental concerns heavily and reflecting social pressure towards adopting green technologies. This suggests that policies like subsidies or carbon taxes could be effective in promoting greener alternatives. Also, the model underlines the importance of social norms and financial capabilities in the decision-making process for heating systems, highlighting the role of community behavior and environmental commitment in adopting sustainable technologies. So for the future technical development of agent-based models, first main part is the advanced intelligence to reach reality, which means the psychological realism in agent-based models. And the second part is to change from individual to collective decision-making. Collective decision-making has the advantage of drawing from the experience and perspective of a larger number of individuals. Hence, they have the potential to be more creative and lead to a more effective decision. In fact, groups make sometimes achieve better results beyond what they could have done as individuals. Groups also make the task more enjoyable for the members when the decisions is made by a group rather than a single individual. Implementation of the decision will be easier because group members will be all join in the decision-making process. And if the group is diverse, better decisions may be made because different group members may have different ideas based on their backgrounds. So that's what we want to do in the next step. And here's a general framework of one type of collective decision-making, which is reaching the consensus. Also, we can do like voting, ranked choice voting, or dot voting. So thanks for listening.